Hello everyone. So here's the next problem. So this is again on RC transient circuit. So as shown in the diagram, so you have one voltage source, one current source, and three resistors, and a capacitor is connected as shown in the diagram. And it says at t is equal to 0, right? This switch is open, right? This switch is disconnected. So it will then, if you open the switch right at t0, then it will simply isolate this part of the circuit. This is gone. It will be isolated, right, once you disconnect that circuit. And then it's asking now how does the capacitor discharges over time, right? So it's basically the question is at t is greater than 0, how does the voltage across the capacitor changes over time, right? And also current across the current for the capacitor, right? So let's do this problem. So at t is equal to 0, right? So what will be this is gone. This is isolated now, right? So your equivalent circuit will be something like that. You have a capacitor. So this is simply an electrolyte capacitor of symbol, something like that is simple polarized electrolyte, polarized capacitor. You have this, and you still have a current source, right? So this is a 2.5 microfarad capacitor, and this is your 6 kilo ohm, and it is delivering. This is a current source which is delivering a constant 2 milliamps of current, right? And now it was charged. So we assume that before time is t is less than 0, right? We assume that this capacitor has already reached the steady state. That means the capacitor is already fully charged before you disconnect this switch, right? That's the thing we have to assume. And we'll have to find what was the initial voltage on the capacitor before you do this, right? So which we need that later. Okay, now what you need is this voltage, right? Voltage at this node is VC, right? That's what you need to find with respect to 0. So let's see that this is your IC, current through the capacitor. This is, let's say, I1, and this is 2 milliamps. So at VC node, let's apply KCL, Kirchhoff's current law. It says, so you have 2 milliamp, right, is equal to I1 plus IC, right? So 2 milliamp is, I1 is simply VC over 6,000, 6 kilo ohm, plus IC is C dVC over dt, right? And right away you can see you get one differential equation. So just rearrange that, simplify that. Simplifying it, right, gets you in our standard differential equation form will get you this 67 V of C is equal to 800, right? Okay, now it has a solution of this type. We know the standard solution of that, right? The solution for this differential equation is VCT is A over alpha plus some constant E minus alpha t. So what is A? This is your A. This is the coefficient alpha. So VCT is A is 800 divided by 67 plus K E minus 67 tau, right? T. So that's going to be your 12, right? Yeah, 800, so 12 plus K E minus 67 T, right? Okay, so let's call this equation number 1. So you still need to find out the value of this unknown constant K from the initial condition. So now the initial condition is, we have to apply initial condition to find that out, right? K. So initial condition is at t is 0. What was the voltage across the capacitor at t is equal to 0, right? So then you'll have to go back to the circuit. Go back to the circuit and put this battery, right, as it is at T0. Now you have to find this voltage. What is this voltage here, right? So now we have to do one more nodal analysis. You can say at T0 minus must be equal to 0 plus, right before you close open the circuit, and right after you close right after you open the circuit, right? That voltage across the capacitor must be same, right? Because okay, so now let's do that. So your equivalent circuit will be, you have the battery, right, and you have this 6 kilo ohm, and you have 6 kilo ohm here, and the capacitor simply works as an open circuit, because the switch was here for a long time, right? The switch was here for a long time. The capacitor simply works as an open circuit, right? Steady state, because the capacitor is already in its steady state. So just to understand, the capacitor acts as an open circuit at its steady state. It's already fully charged, so current doesn't conduct. It works as an open circuit, right, at steady state. Okay, so these are the 6 kilo ohm, and this is 6K 2 milliamp. Okay, so now you have to find out this voltage, whatever voltage at this node right here, right? This is a 9-volt battery, right? This is a 9-volt battery. Yeah. So the voltage here is 9 volt, but this is your VC at T0. So somehow you have to find out that one, and that's easy now. Just use the nodal analysis, right? So I'm going to call I1, I2, I3, and this. So at VC, which is this, right, this node, what is the Kirchhoff's current law? So I1 is coming plus 2 milliamp is coming, right, is equal to I2 plus I3, right? Total current entering must be the total current going. So what is I1? I1 is 9, this I1 is current here, right here, right, is 9 volt minus VC, right, divided by 6 kilo ohm, right, 6,000, plus 2 milliamp is, you cannot do anything, plus I2 is, again, I2 is VC over 6,000. I3 is VC again, right, because voltage here is VC. This is the reference. Make sure you first choose the reference node here, right here. VC divided by 6,000. Okay. Now simplify that, right? I would simplify this, and I'm gonna, let's see, yeah. So then you simplify that, right? Again, you work on this algebra, simplify it, and you will see that the voltage across the capacitor is turned out to be 7 volt at T is equal to 0 second, right? And now this is the condition we're going to go back to this differential equation, equation number 1. So from equation number 1, right, again, we call it equation number 1. So voltage across the capacitor was 12 plus K E minus 67 T. Now apply this initial condition at T is equal to 0, 7 volt, right, is 12 plus K 7 T. So and this is 0, because T is 0, right, and E0 is 1, right? So 7 is equal to 12 plus K. So that means the value of that unknown constant K is -5, right? And your general solution for the voltage across the capacitor becomes 12. So K is -5. So 12 minus 5 is -67 T. And if you want to do in terms of time constant, it's fine too. 12 minus 5 So what is your time constant? Time constant is simply 1 over 67. Right? So 1 over 67 is, in terms of millisecond, is about 15 millisecond. That's the time constant, right? So E negative T over 15 millisecond and volt, right? So this is how the voltage across the capacitor changes in this particular circuit. And if you plot this carefully, so this is the voltage across the capacitor as a function of time. You need at least 5 time constant to reach the steady state. So what is at t? So from this equation, at t is 0, right? Just when you open the circuit from the given circuit, the voltage across the capacitor is 12 minus 5, right? Because E0 is 1, right? So 12 minus 5 is 7, right? And at t is infinite. Infinite means if you wait long enough time, right? Then e to the power infinite, 1 over infinite is 0. So it's 12 volt. What we see is this becomes 0. This becomes 0 if you wait long enough time, right? Because 1 over infinity is 0. 12 volt. So 12 volt is the steady state. So if you want to plot that, it will be something like that. So it starts from with 7 volt, right? 7 volt, and it will increase, and steady state will reach at 12 volt, and it starts with 7 volt, right? So it's in millisecond time. Okay, so this is how this circuit behaves, right? So this is how. So it's not a discharging; it's still charging because you have current source here, right here, right? Even if you isolate the battery, right, the voltage source, since because of this current source, it's not a discharging circuit. It still charges like this.